Okay, as promised, I'm going to start talking about work in physics. Okay, the work in physics is not the same kind of work as you do at your job. It's not the same kind of work you do when you're doing yard work all day. Although occasionally actual physics work happens when you do those things inadvertently. Okay, so work happens every time a force is applied to an object and that object covers some distance. Okay, so if I apply a force to this object and it moves some distance d, I've done work on it. Okay, so the definition, the physics definition of work is just the dot product between the force and the displacement vector, right? Which you may remember is the magnitude of the force that you apply times the magnitude of the displacement times the cos of the angle between them, right? And so you might wonder, why not just force times distance? Why this cosine theta? Why do we care, right? So let's suppose that you're dragging a box. Well, you're going to take a real simple example. Okay, you're dragging a box. And so here is you, right? And here's your little rope, right? And you're dragging the box with your little rope. Okay, and so obviously here, the force you're applying is in this direction, right? But you're actually moving the box in this direction. All right? So you have this kind of weird situation where force is up here, right? But your displacement is down here. Okay? Now, this displacement could be this big, it could be just a little displacement, it could be a big long displacement, it could be whatever, right? It doesn't have to be as long as this, as I drew this force vector. It just depends on how long you drew it, you dragged it, right? But one thing you have to remember is that there's two components here, right? There is an fx component, all right, a component that's pointing in the direction of d, or there's an fy component, the component that's pointing perpendicular to d, okay? This component here is not doing any of the work, right? If something's moving in this direction, this component has nothing to do with it, right? So we have to toss him, we have to find a way to toss him to the side, okay? And we have to focus specifically on the component of the force that's in the same direction as the displacement, okay? That's where this theta comes in, okay? So as you know, if that's the angle, the component that touches the angle is the component that's parallel to the angle, right? Well, that's parallel to d in this case, okay? So in this case, by multiplying by cosine theta, you're getting the component of f that's parallel to d, that's in the same direction as the displacement, okay? And that's why we have this cosine theta. That's why it's a dot product. That's why a couple lectures ago I made you learn dot products, okay? All right, so once again, in summary, we have to isolate the component of the force that's actually in the same direction as the motion, because that's the only part of the force that's actually contributing, okay? So this is why whenever we're calculating work, it's going to be FD cosine theta, where theta is the angle between the displacement and the force vector, okay? Couple things. The unit of both work and energy. So work, when you do work on an object, you're giving an object energy, right? So the units have to be the same. The units of work and energy are both joules. So for example, if I'm doing work on this object by making it move, well, look at that. I've suddenly given it kinetic energy because it's actually moving, right? So that's why I kind of like to keep the analogy of energy being a currency. So you could say that forces are the bosses of the universe, right? The people that pay you or that pay objects, right? They hand out energy money in the form of work when they act on objects. So if I'm a force, I'm acting on this object and I'm giving it an energy currency. I'm giving it energy money in the form of kinetic energy. Okay? So a couple things. We can think of work, if you go to the next slide, as the currency that a force gives to a body when a force acts on it. This currency is called energy. When gravity acts on a falling object, it does work and gives the object kinetic energy. Okay? When a piston squeezes a gas, it does work and gives the gas thermal energy. Okay? When Scott lifts weights, he does work and he gives the weights potential energy. Right? So in all cases, when you do work on an object, right, a network on an object, you're giving it some form of energy, currency, right? There's many different types of currency you may be giving it, but it will be some type of an energy currency. All right. Pro tip. A force does positive work whenever it has a vector component in the same direction or less than 90 degrees with the displacement. All right. So positive work would be a situation where I have a force here, a displacement here, right? And this angle here, less than 90 degrees, that is positive work. But what if you have a situation here where the displacement's in, let's say this direction, right? But the force you're applying is over here in this direction, right? And this is, theta is greater than 90 degrees here. So this is less than 90 degrees, and this is greater than 90 degrees. In that case, you're doing negative work, okay? So it does negative work when the vector has a component in the opposite direction or greater than 90 degrees, and it does zero work when it has no vector component that's pointing in the direction of distance, right? So kind of like what we were saying before, if the force is in this direction, right, and displacement's in this direction, this force is doing no work on the object, okay? So that is a general introduction of work. We're going to do one misconception question here, and then we're going to move on to a question in the next video, right, to kind of put this actually with numbers. Okay, misconception question number 2. You push very hard on a heavy desk trying to move it. You do work on the desk, A, whether or not it moves, as long as you are exerting a force. B, only if it starts moving. C, only if it doesn't move. Or D, never, it does work on you. So you can tell from this equation that you've only done work, right, if the object has actually moved some. Okay? In this case, if you did not get some displacement by moving the desk, you are not actually doing work on it. Okay? You guys are very curious about how this might be applied to a certain physical problem, and in the next video, we will talk about the ant who dragged the moth.